In this video, I share my work for a practice exam covering content from the first chapter. Here are the 10 different questions that I'm going to go over, all of which are very representative of ideas that you'll find within chapter 1. First one, you're developing a new procedure to measure the density of gases. It says you measure nitrogen gas and obtain a particular value under particular conditions of temperature and pressure. Is the approach you used accurate? First thought, I'd pause without reading any of the choices, consider what is accuracy? What does it mean to say a procedure would lead to accurate or inaccurate results? Accuracy is different than precision. Accuracy, as the book states, refers to how closely individual measurements agree with the correct or true value. So in order to determine the accuracy, we need to get a sense of what the value was supposed to be. So what would we do? Would it help us to repeat the same measurement and then compare the two results? That kind of comparison, I think, would give insight into precision, but not accuracy. Second, consult a reference source and find out the accepted value. I like that because now we can make a comparison between what we did and what the true value is. Analyze a different amount of nitrogen and compare the two results. I don't like that one because it's not giving us a comparison with the true value, so I think the second choice is the best. Which of these is an exact number? Select all that apply. Before reading the choices, I'm going to pause and think, well, what is an exact number? Going to the textbook, we find that there's two kinds of numbers that we're going to we're going to meet up with. We'll meet up with exact numbers, those whose values are known exactly, and inexact that have some uncertainty. Numbers that are obtained by measurement will always be inexact. Looking at our choices, number of inches in a foot, that's an exact relationship. There's exactly 12 inches in a foot. Conversion between inches and meters, that's also an exact relationship. An important one that we want to know is listed right here. 2.54 centimeters is defined as being exactly 1 inch. There's no uncertainty in that. It's an exact relationship. So we could use that relationship as we set up some dimensional analysis here to get a relationship between inches and meters, because metric conversions are also exact. It's exactly 100 centimeters in 1 meter. That's how it's being defined. So the conversion factor going between inches and meters, turns out that also is exact. Number of people in Ohio, volume of water in the world's oceans. I think that both of those need to be measured in some way. So I think the only exact ones are A and B. The idea of being measured in some way, there are some things that we could count, such as fingers in your hand, on your hand, 1, 2, 3, 4, 5. I don't think there's going to be any uncertainty in that. I think you could exactly count that. But if we're trying to count the number of people in Ohio, I think we have to do some kind of sampling, some kind of measuring. In theory, it is a particular exact number, but by the time you start counting, by the time you finish, you've had people enter, leave the state, babies born. So I don't think the number of people in Ohio would be something that could be exactly counted. It had to be measured in some way. Here's an end of chapter question that is on the same point. Here's a particle level representation. We have 3 different responses to fill in. This image depicts a physical change as we have a particular compound undergoing a physical change, and we still see that same compound here. To me, this is describing a particular compound where I have 2 different elements present, existing as a solid and then existing as a gas. So I think this is a physical change in which a compound is being transformed to produce another representation of the same compound, but now as a gas. Kinetic energy of an object is calculated with the formula of kinetic energy equals 1/2 mv squared. If the velocity of the object increases from 10 centimeters per second to 1 meter per second, how much does the kinetic energy increase? Have to be careful here because we have different units involved. First thought is, let's convert 10 centimeters per second into meters per second. So here would be my conversion factor for that. So the comparison now is something initially going 0.1 meter per second increased to 1 meter per second. We could take those and put them into the equation. Kinetic energy equals 1/2 mv squared. The velocity, the meters per second part, is being squared. So we could see what the resulting joules for the energy would be. Setting up a ratio, we find that it's increased 100-fold. You might have also been able to look to see the difference between 0.1 and 1. That you've moved the decimal one time, a difference of 10-fold, and since we square it, it becomes 100 times different. Perform the calculation and report with the correct number of significant figures. Really typical learning objective here, a mixed operation significant figure calculation. Within these, we've got to be really careful, especially when it comes to addition and subtraction. We want to stack those up. So first of all, looking at each part, we have multiplication going on. So I would take what the calculator gives me for the entire value for each of the different multiplication applications, and then recognize the one on the left is going to have 4 significant figures, and on the one on the right, it would have 2, coming from the 0.050 that has 2 significant figures. If I keep all of those terms, and I'm not going to round yet, I'm going to only round at the end, I see that the first value is significant to 1 decimal point. The second value is significant to 2 decimal points. So if I take my entire value, it can only be significant then to the first decimal point. So I would take it, and at that point, I would do my rounding. I know the key error students would make in this would be failing to account for the subtraction properly and by not stacking up the terms. Here's a scenario. So we have a small beaker containing some liquid. Some of the liquid's poured out, and we have a new mass for that beaker plus liquid. A density is given for the liquid, and we're asked about the volume. So I'd first think, okay, this is about significant figures. Tells me in the question, report it with the correct number of significant figures. So I want to apply all of my rules. So I initially have a beaker plus a liquid, which is 35.15 grams. We pour some of the liquid out. It's 29.65 grams afterwards. So I would have 5.50 grams of liquid poured out. That would be good to 2 decimal points. All those digits are now significant. So now we can use that with our density term. It says that it has a density of 1.053 grams per mil. The sample we used was 5.50 grams. I could use my density to convert, figure out what the volume would be, and then report that to 3 significant figures because the measured value here gave me 3 significant figures. A body of water holds 100,000 liters of water. We've got 2 of the dimensions, the width and the length. How deep is it? As I look at this, my conversion between units of volume like liters and units of length is this definition. 1 cubic centimeter is exactly 1 milliliter. And I'm thinking I need to be careful with cubic units. So I know that it said that it is 100,000 liters. What would be that volume in cubic meters? So I'm going to start with what we know and move towards what we want to find out. So I could convert from liters to milliliters. Back to that definition where 1 milliliter is 1 cubic centimeter. And then there's 100 centimeters in every meter. But the cubic part, I want to be careful because this entire part here gets cubed, this entire conversion factor. So that would lead me to find that the volume in cubic meters is 100 cubic meters. The pool has a length, a width, and a depth. 2 of those components are given, 25 and 10 meters respectively. We don't know the depth, but we know the product of all 3 of those is 100 meters cubed. So the depth here would be 0.4 meters. That would be my missing term that I have in there. I'm using only 1 significant figure because if I look within my measured value, 100,000 only has 1 significant figure. Which of the following leads to new substances being formed? Chemical reaction, melting a solid, chromatography, or freezing a liquid. New substances are formed when we have a chemical reaction. Melting a solid would be a phase change, such as an ice cube becoming liquid water. Freezing a liquid, that's also a phase change. Chromatography, that's separation of a mixture. Filtration, distillation, chromatography are all ways to separate a mixture. And when we separate a mixture, we're not making a new substance, we're just separating out the ones that are there from each other. We have an instrument that measures some property when the sample is tested, and we want to know if that property is an intensive property or an extensive property. This would be one where, before reading the choices, I'm going to think, well, what are those intensive and extensive properties telling me? So extensive depends on the amount of matter that's present. The mass is an example. When you have more matter there, the mass is larger. Intensive is independent of the amount of matter that would be present. The density would be an example of that. Given the choices here, what if we made repeated measurement on the same sample at different temperatures? I'm not sure that would help us. I don't think that looking at the same sample by varying the temperature, we're not varying the amount of matter there, so I don't think it would give us any insight. Analyze the same sample at different temperatures? Well, volume, that's an extensive property that usually changes with temperature. The mass of a solid is an extensive property that does not change with temperature. So by looking at it at different temperatures, that doesn't really narrow it down for us. Density, it turns out, is an intensive property that changes with temperature because one of these, the volume changes, whereas the mass would not. So my point here is that we've got a combination by varying the temperature. Sometimes it might give us some change in value for the property, but that doesn't mean it's intensive or extensive. Analyze different amounts of the same sample at the same temperature. I like that because we could see under the same experimental conditions if varying the amount that we have changed the value for the property. If it did, that would make it an extensive property. Final question, which of these is best described as a homogeneous mixture? Before reading the choices, what is a homogeneous mixture? We have more than one substance present and they're evenly distributed throughout the sample. More than one substance is making it a mixture, and the evenly distributed part makes it homogeneous. I think salt water is the best description, best example. An egg, I think I have different substances present, but it would be a heterogeneous mixture. The yolk of the egg is different than the outer shell. Different parts have different compositions. So I'd view that as being heterogeneous. Sugar cube, I describe as a pure substance. Helium gas, also a pure substance. Here's some examples of taking everyday objects, things that we might encounter, and then classifying them using different terms like pure substance, like mixture, whether it's homogeneous or heterogeneous. Summary of these 10 questions. All of these topics and questions are closely aligned with learning objectives from the textbook. It's important to self-assess yourself. Would you say you've mastered all these topics? Would you be able to explain them to a classmate? If so, then you're definitely on the right track. If you have gaps in your ability to explain, if you feel like you truly haven't mastered the topics, don't wait to improve. If you've identified weaknesses, now's the time to act on them.